here. In this lesson, we shall focus on MAM2013S UCT Introductory Algebra module. We shall look today at an overview of the entire module. We shall discuss every single part that must be known until such time that the exam is written. But the approach is going to be focusing on how we need to solve examination questions. Right, as usual, the analysis is going to be based on the structure of the 2022 2-hour exam that was out of 80 marks. And where you have to read the instructions carefully. You have 2 hours to complete the exam. Make sure that no pages or questions are missing. Show all your work or reasoning. Answers without work or reasoning shown will receive no mark. Right, so this is exactly the backbone of our discussion today. Right, so there are some things you have seen. For example, right, given let G be an arbitrary group, right? So if G is just an arbitrary group, right, and A and B are members of G or elements of the group G, right, for 10 points, it becomes significant to be in a position to use induction. Okay, the principle of induction is very significant in this module, as basic as it is, but it is actually often used in many instances in this module. So for 10 points or 10 marks, often than not, students are expected to be in a position to use induction to prove a given result. For instance, what are we supposed to prove here? We're supposed to prove that B times AB to the power n minus 1 times A is equal to BA all to the power n for all n greater or equal to 1. Right, so this becomes very, very interesting. But also, you see, the question is, how easy is it to prove algebraically? And also, obviously, how easy is it to prove by the principle of mathematical induction, the PMI? Right, so we actually then focus on the proof. So we shall first look at part A. For example, we take note that our n is greater or equal to 1 for which this is true. So now we can start and then say, for instance, for n greater or equal to 1, we let P subscript n be the statement. Right, be the statement. What statement is this? All right, be the given statement, this one. Right, which is a statement B, AB to the power. You can write this at the bottom. So if it is the statement B times that, so it is a statement B, AB to the power n minus 1A is equal to BA to the power n. Right. So we know that it is, okay, if we are dealing with that statement, it is clear that P1 is true. It's clear that P1 is true since, okay, yeah, if you make 1 there, gonna be BAB 1 minus 1A. Then now you have exactly what we're getting. What are we able to achieve here? So if you have AB to the power 1 minus 1, what are we able to achieve at the end of this? So it becomes AB to the 0th power A, like this. Right, because these elements here are elements which are, okay, there are a couple of ways, obvious, to reason that out. So you can actually obviously refer to this as a being to the 0th power. Simultaneously, it is actually obviously one can look at the fact that it is the same as the following, which I believe is best for our analysis. To write it as follows. So you can write it as AB and then AB minus 1 like that. And it is then exactly A. All right, now we are multiplying an element by its inverse. So if you're multiplying an element by its inverse, obviously dealing with an arbitrary group, so this would give us the identity in the group. Depending on the notation, so you would have B, the identity, and normally identity can be called E, but yeah, it actually depends. You can even call it 1. Right, we can even call it 1, which I believe would be right. So yeah, we can call it 1 in this case. Why? Because you can see, assume that this is 1 for M, to show that this is 1. So in this case, therefore, it is possible to then say the identity itself is 1, or you can call it E. E is very popular in most of the books, and yeah, I'll actually cross-check again in the notation of your book. So obviously, with this exactly in this notation, this would be exactly a BA. And with that mentioned, we are able to see, therefore, that it is actually BA, but it is BA to the power what? It is actually BA to the power 1. All right, so yeah, it is therefore true for n equals 1. It is clear that P is true. P1 is true, which means it is BA to the power 1. It is BA to the power 1. So in obvious, I mean, it confirms the truth of this, and it is true. Okay, since this is the case. And that implication obviously is then that if we have BA to the power 1 minus 1A, like this, when n is replaced by 1, substituted by 1, it is therefore BA to the power 1, which is exactly of the form required, that if we have AB in the middle of the B and the A to the power n minus 1, it is BA to the power 1, right, where the n is 1. So indeed, this result is true for n equals 1. Now, obviously, the next step here is the induction hypothesis step. Right, so now the step we're dealing with here is called the basis. It's called the basis step. So we're focusing on the basis step. Okay, there are many ways of writing the basis step. I mean, a student can just say let n be 1 and show that the left and the right are equal. Right, and avoid a lot of the writing here. But simultaneously, then the next step is the induction hypothesis. Right, so we look at the induction hypothesis step. And now, if you look at the induction hypothesis, it is as follows. Right, so induction hypothesis. I know that this is basic, but it is part of this. Right, just an overview of the whole section, of the whole module. Right, so in view of the induction hypothesis, that as well obviously must be, learned and remembered, we begin as follows. And we always start by an assumption. We suppose now that PK is true. That is, right, we suppose that PK is true. And now the truth of PK means that a replacement of n by k renders a true statement, which means therefore we'd have BAB to the power k minus 1 a, and this is equal to BA to the power k, like that. Right. Now, and let us show that. Right, so let us show that pk plus 1 is true. I just want to discuss, we're just discussing this. It's just an overview of the whole module. Right, we need to show that, let us show that pk plus 1 is true. Okay, because we assume that pk is true and we show that pk plus 1 is true, that this principle of this statement is true for the successor as well, for the pk plus 1. So it's also true. Right, so we want to show that the pk plus 1 is also true. So we actually get on the bandwagon and we then say, in fact, right, in fact, what we're able to establish here becomes exactly as follows. Okay, so it's an interesting, obviously, principle. So we start with the left. So we've put, right, in fact, k, n equals k plus 1 yields. Right, so you're going to start and write b to the n minus 1, which is b, ab. In the place of n, you put what? You put k plus 1 minus 1a, like this. And so what is all this here? What is all this here? So in the place of n, you have put the k plus 1. Right, and what does that yield? Right, it yields b, a, b, and then you have kth power a. Right, the 1 minus 1 becomes a 0. Becomes exactly a 0. And so, what is this? Okay, sometimes it can be tricky to play around in a way that is productive. But now you can actually be able to write b, a, b, and then you can be able to write ab to the power k minus 1, then a, because yeah, the power 1 here and the power minus 1 there, they cancel out, giving us just ab to the kth power, and you still have the b and the a on the extremes. Okay, yeah, that's good and that's clear. All right, so what is the meaning of all this stuff? As a consequence, what we're then able to get is we have that this then equals, moving across, we're able to see, therefore, that we can be able to write a BA. And then there's a B. Okay, yeah, BA is, B and A are put together. Then there's a B. And then, right, so now let's check this. So if we associate by association, by the associative law, we are in a group, so we can apply the associative law. So we associate B and the A, and we have BA put together. Then we have this B, then AB to the power k minus 1, then we have the A. What is all this? What is all this stuff here? Okay, let us. Yes. What are you able to see? Yeah, I'm sure that
gives us.
Yes.
It gives us what we wrote the pk. It gives us yeah.
Exactly this. Yeah. B to the power, yeah, because the B A b to the power k minus 1a would give us the BA to the kth power, right? Yeah, that is correct. Yeah. So which means you can write the BA here, and this here is actually BA to the kth power. Okay, we're good? Yeah. And then, how far are we right now? It is exactly what we desire, because it is exactly BA to the power k plus 1. Yeah. So now we started with the k plus 1 here, and we have the k plus 1 there. And in other words, we can even with confidence, say, yeah, I can write it at the bottom. We can even with confidence say, what actually were we supposed to like show exactly? We're supposed to show that if you have the b, ab to the power k plus 1. So in the place of the n, you put k plus 1, then you have minus 1a. It is always the same as b a to the power k plus 1. So if you have the k plus 1 in the place of the n here, it would be b a to the power k plus 1. So yeah, this is actually what we have. But what then is the conclusion by the PMI? Right. So we conclude as follows, and we say by the PMI. Right. By the principle. Right. By the principle of mathematical what? Induction. Okay. We're just practicing this anyway. We're still going to go deeper into the sections that are important. We obtain, by the principle of mathematical induction, we obtain that Pn is true for all n greater equal to 1. Yeah. Okay, we've just established that by the PMI, it is right. We obtain that Pn is true for all n greater equal to 1. Let's look at the next point. Assume that AB, okay, I'm playing around with this, is always very, very interesting. Just some basics on the groups. Now, assume that AB to the power m is 1. Okay, so AB to the power m has order 1 for some n greater equal to 1. Yeah, so we then say the AB to the power m has order m. Excuse. So it is order m. Right, so if then we assume that the AB has order m, so that we've raised to the power m, then get the identity for some m greater equal to 1, use A to show that BA also is order 1. Wow. Okay, this is profound. Okay, now obviously, I mean, to be very interesting because this group is arbitrary. I mean, in an abelian group, yes, you would say for sure because AB is equal to BA in an abelian group, but this is arbitrary. So it's a group, yeah, that has not been stated explicitly as arbitrary, right? Provided you can be able to just establish that from some of these properties here, you can prove that this group is abelian. Okay, meaning it's a commutative group. Okay, anyhow, so we're gonna actually proceed with using B, using the fact, right? Using that we're given that AB to the power m is 1, like that. And we're using that together with, right, using that together with A, yeah, that one, that relation there. We have that. We have that. Okay. So in other words, let us use this set. We have that if you write AB to the power m plus 1, it is equal to what? Okay, that's interesting. So this one, you can be able to, if you raise the AB to the power m plus 1, or rather, right, if you raise BA, excuse, right. Okay, let's first write BA. Okay, you're going to obviously be able to see because we need to show that this BA is 1, but we're starting with AB. Right, we need to show, so yeah, let's start with the BA and raise it to the power m plus 1. And what is this? So if you have BA to the power m plus 1, according to this, it's going to be BAB to the power m plus 1 in the place of the n, and then you subtract 1 and then you put a like this. So which means that it is b, ab to the power m, then a, right? So what is this? Right, by the principle we have, whenever you have exactly the b, ab to the power m, a, it is exactly the same as what? Right, so I want us to look at this very, very carefully and analyze it together. We have already seen that if ever this is the case, if there's an n minus 1, then you have exactly an n. And so we agree, therefore, I want us to look at the fact that this will indeed simplify to BA. Right, this will indeed simplify to BA. Why? Because, you can write an intermediate step here. Because the AB to the mth power is just 1. Okay, yeah. Because the AB to the nth power, we got to this, and the AB to the mth power is 1. So that indeed this is just BA. And then by the right cancellation law, right, doesn't matter. So obviously, I mean, this has implications on the fact that this is BA to the mth power, and then you can break it down to this. Well, it doesn't really matter. You can write it like BA. And then what is all this here? Okay, you can write it even the other way around. I mean, it's not restricted to only this form nature of multiplication, but then we have BA to the mth power. BA, then you have BA inverse. If I put the BA on the right, it's going to be BA inverse. BA, then BA inverse. Right, so which means that you have BA, the n power. Okay, this one is the identity. And this one is also the identity, which is 1. So indeed, it is true that if AB to the mth power is 1, also BA to the mth power is 1. Okay, this is nice, but yeah, it's very interesting. Yeah, there's a way to use the fact that this is true. But yeah, in other words, you see, this is true in an arbitrary group, meaning in general, you really can be able to establish that it is true for all groups. For all groups. Okay, yeah, it's exciting. Let's move to the next point. We move to the next point. Right, let's move to the next point. All right, now let us discuss some of these. Also, we shall actually be delving into the chapter 3 or about groups, and we shall spend time on those different groups, like the groups of equilateral triangles, those groups of symmetries. Okay, we shall spend time on those and rotate those and flip them and so on. Okay, but in the meantime, we are then saying in each case, for example, in each case, determine whether the statement is true or false. You'll get 0 marks if you do not provide an argument for putting your answer. Right, so we need the truth or the falsehood of this. But now you'll get 0 if you do not provide an argument supporting your answer. So if we state true then or false, we must bring justification on board. So yeah, it's awesome. Let us start with the first question. Suppose that m and n are 2 positive integers. We start with m and n as 2 positive integers. If d is strictly bigger than 1, satisfies this particular equation, d equals am plus ban for some integers a and b, then d itself being greater than 1 strictly is the GCD, the greatest common divisor of the 2 integers. Okay, awesome. Right, so the question is, obviously, is it true or false? Well, we shall discuss this, but it is actually a false result, and we shall bring justification for that. So first things first, we are able to realize that this is false. Right. Why is this false? Right, so it is false because there is a result that we need to learn, and we shall discuss that. And I feel that but I'm going to start by saying, first and foremost, I mean, to be very direct, right, the converse. We note that the converse of right, the converse of what we call the Bezos lemma. Right, the converse of Bezos lemma doesn't hold. We know that, and we're going to state the converse. We're going to state the lemma. Right, but um, to be very direct here, we note that the converse of Bezos lemma does not hold. First things first. Right. And we shall justify that with an example. So we then say, take, take for example, we shall state the lemma shortly. Right, take for example, let's take two instances where we then say m is 4, n is 8, m is 4, n is 8. Okay, like this. M is 4, n is 8. Right, if D is strictly bigger than 1 satisfies this, then for some, then integers A and B, then D becomes the greatest common divisor of the M and N. So now we'd have to look for the GCD. We'd have to look for the GCD of the two numbers, M and N. M is 4 and N is 8. What is the greatest common divisor of this? Surely the greatest common divisor of 8 and 4 is 4. Right. And we note that, we note that 12 actually satisfies that. Satisfies that if you look at this particular equation. Right. So in other words, if we then say what are the A and the B, if we let A be 1 and M and N, M is 4, B is 1 and N is 8. 4 plus 8, like this is like 4 plus 8, which is 12. Right. So, right, we have taken A and B to be 1, and the result is obviously then 12. Right. And so now we're able to then see clearly that 12 satisfies this particular equation. Does it then mean that 4 equals 12? Right. So, in other words, you really can see that if the greatest common divisor, it says that if this is the case, if D is equal to this sum for some integers A and B, then this is the case. So here we have that if ever this were true, it would mean that if ever 12 is this here, does it therefore mean, and obviously, does it therefore mean that 12 is the greatest common divisor of the M and the N, 4 and the 8? Obviously, it is not true, this. Right, so since this here is not true, then we are excited to then say, indeed, this is not true. So we have this, but yet 12 is not the greatest common divisor of 4 and 8, because we saw that the greatest common divisor of 4 and 8 is 4. So indeed, this is actually a false result, and it is We note, therefore, that we are yet to look at the formal statement of what we call Bezo's lemma. And now it's a lemma that I'm sure that will be, I want to use exactly the same wording as it is used in your material, in your textbook. I think that what I'm going to do, because I want to just highlight something about the Bezo's lemma, right in a split second, I think that I'm going to actually give a comment on it, so that you are able to. Okay, let us have a statement of what you call the Bezo's lemma. Just a little bit. Right. So now, if you look at what we call the Bezo's lemma, right. Bezo's lemma. We have the statement as follows. Popularly, it is stated like this, and you say let. You let A and B. Let A and B be integers. Let A and B be integers. Right. With greatest common divisor, with greatest common divisor D. Okay, if that is the case, we then say then there exist. Right, there exist integers. There exist integers, x and y, such that this equation is 2ax plus by equals d. Okay, I want us to look at this and pause for a minute to internalize it. Under this, okay, Bezo's lemma. Right, Bezo's lemma. Let A and B be integers with greatest common divisor D. Let A and B be integers with greatest common divisor D. Okay? Right, so we note that. So we take A and B to be integers with greatest common divisor D. What does it mean? Well, in the notation, it means that you have the greatest common divisor of A and B is equal to D. Right, so this is sort of what this statement is saying in words. Right, so you have A and B are integers with greatest common divisor D. So we have this equation. Then there exists, right, there exists integers x and y such that we can have ax plus by is equal to D. So this becomes Bezo's lemma. Right. So yeah, just take note of the lemma there. Right. We continue. Right, we continue. Right. Okay, we continue. We actually moving on. So we're just stating the lemma. The lemma starts with what? Bezo's lemma starts with the GCD of A and B. So if the GCD of A and B is D, then we can find some integers x and y, which are integers and not just any real numbers, which can be fractions, etc. Not any rationals, but integers, such that ax plus by is the greatest common divisor. So now we continue, please. Okay, just letting Bezo's lemma. Now, The set of all permutations, S3 is an abelian group. Okay, very, very interesting with this one. Now, let us take a look at this here. And now, as the symmetric group themselves are very, very interesting. But now, they don't like being abelian, this. They don't like being abelian. So, but yeah, so this one here is false. Is false. The set of all permutations S3 is an abelian group. Well, S3 is not an abelian group, and so we need to provide justifications. We continue. We continue. Okay, okay, we need to bring some argument to support our answer. Obviously, the symmetric groups themselves are generally not abelian unless otherwise. For some elements, maybe. Okay, right, which can be true for some elements. So now let us speak about the transpositions. The transpositions. Right, the transpositions, alpha equals 1, 2, and beta 1, 3. Okay, that's okay. We're looking at the transpositions. Transpositions are cycles of length 2. Right, so if you look at these two transpositions of cycles of length 2, right, the transpositions are in SN, and they they do not commute. Very important. They do not commute. So we know that 1, 3 and 1, 2 do not commute. Okay, if they don't commute, we need to explain why. But how so? And we need to show they don't commute. In fact, if you look at alpha, beta, alpha is 1, 2, and then beta is 1, 3. Okay. 1. Okay, because each one of these is 1. We're able to see that we have 1 here. We start with the 1. Didn't start anything. Starting with 1. Then 1 goes to 3. Right, and we're able to see that. Right, so if 1, we're able to see that 1 goes to 3, and then if we have 3 here, we are able to immediately see that indeed 1 goes to 3, and simultaneously we're able to see that in this cycle, okay, 1 goes to 3 in this cycle, but where does 3 go in this cycle? Right, because we want to relate that. So 1 goes to 3, but 3 goes to itself. In this particular cycle. Right. And we then continue to then say, if you then, what is the next element that you actually have? Right, because 1 goes to 3, but 3 goes to 3 here. Right, and simultaneously you are able to see that your 1 goes to 2. Right, and you're able to see that your 1 goes to 2. I want us to discuss this a little bit more at length. Right, we know that if you have B alpha, okay, what is beta? 1, 3. Okay, we shall discuss these permutations in the cycle. Yeah, we can even discuss them like, okay, feel like we need to elaborate on these a little bit more. Okay, let me just explain these as follows, just to make sure these makes the kind of sense I wanted to make. All right, so let's just explain these a little bit more like this. To say, in fact, okay, let us look at alpha beta. Okay, and then you look at alpha, which is 1, 2, and then beta 1, 3. Okay, and then we have 1, 2, 3, and then you have 1, 2, 3. Okay. Right, I want us to write these differently. We have to spend a bit more time, obviously, on this, but right, and then you'll be able to see that in the first permutation, 1 goes to 2, and you can say also 2 goes to 1, and then you have 3. Right, and then in this one here, we have 1 goes to 3, and then here you have 3 goes to 1, and then 2. Okay, 2 goes to itself, and 3 goes to itself. Now, when you get to this point, you'd have 1, 2, 3. Know that obviously it's a course where this is learned. Yeah, but it's learned in multiple levels. First year as well. Right, so now if you then say, normally you start from the very end of this, in reverse. So you have 1. 1 goes to 3, but 3 goes to 3. 2. 2 goes to 2, but 2 goes to 1. 3. 3 goes to 1, but 1 goes to 2. So you can convert this one to a cycle notation. And obviously, you can find much nicer ways to do that. So if you start by writing 1, where does exactly the 1 go in this case? Right, you're able to see that 1 goes to 3, and then you're able to see that 3 goes to 2. Right. So this is what you're getting. You're able to see that 1 goes to 3, and 3 goes to 2. So in these particular cycles, in this particular cycle of length 3, you're able to see, therefore, that indeed this cycle means that 2 goes to 1. But 1 goes to 3, 3 goes to 2. Okay, take note of that. Now, I want us to look at the following. Okay, there are many ways you can write. You can even draw these things as a cycle. Right, you can even draw it as a cycle. Okay, but in the meantime, let's look at this. Okay, so that it doesn't go counterintuitive. All right, we can look at the opposites, beta alpha. Okay, yeah. Now the beta alpha can start. I want to write it properly a little bit. 1, 3, 1, 2, and then we can write the permutations in this notation. Right, the 1, 3 can be written like this: 1, 2, 3, 3, 2, 1. We've already seen why that is the case. The 1, 2 is this one. 1, 2, 3, 2, 1, 3. Okay, I know that. Need to always remember these things. Right, so I want to just do beta alpha. 1, 2, 3. Okay, let's see. 1. 1 goes to 2, 2 goes to 2. 2. 2 here. 2 goes to 1, 1 goes to 3. Right, 3. 3 goes to 3, 3 goes to 1. Okay. Yep. So now, what then are we able to achieve at the end of this? Okay, so yeah, we must separate to make sure that these things are not confusing. Right, if we get to this point, if you start with 1, what does 1 go? 1 goes to 2, brilliant. And then 2 goes to 3, and then 3 goes to 1. Yay, we're good. All right, now that reminds me, we had to spend time on this, but yeah, can draw a cycle like this and put the numbers here. Right, to say if you have 1 here, 2 here, 3 there. And say 1 goes to 2, and then 2 goes to 3, but then 3 goes to 1. Forms a cycle like that. So, right, so I think this is nicer. Okay, let us continue, and it explains why these 2 cycles now produce 3 cycles. Okay, we're discussing this. The set of all permutations S3 is an abelian group. it is clear that alpha beta is different from beta alpha. Oh, and this observation is adequate to then say, okay, yeah, S3 is not a billion. Therefore, S3 is not a billion. It's not a billion. Okay, so yeah, take note of that. Let's move to the next question. We're just practicing with these things. By the way, I have to spend a bit more time on the groups and yeah, these permutations of S3, the alternating groups. Let's look at C. Right. Every abelian group is cyclic. True or false? Every abelian group is cyclic. Well, obviously, this one here is a false result, and we explain. It is false. Why is it false? Right. Right, as seen, for example, we'll speak about this class. As seen in class, right, as see, okay, I want to, obviously there are specific notations. I want to speak about the group. The group. Right, the group Z2 cross Z2. Right, is not cyclic. We're analyzing this group and we're going to discuss it a little bit. Okay, this group is not cyclic. All its elements have order 2. All its elements have order 2. And it is a billion. Okay, let's discuss. Okay, if you look at the group Z2 cross Z2, it's cyclic. All its elements have order 2, and it is a billion. Every abelian group is cyclic. Now, if you look at this group, it is cyclic. All its elements have order 2, and it is most certainly a billion. It is most certainly a billion. Anyhow, my point is, what I'm trying to say here. The group is not cyclic. The group is not cyclic. Okay, why? Okay, you can see why that is the case. What are the elements of this group? Okay, I'm sure that you will get to spend a bit more time when we discuss these groups, the free abelian and so on. Now, the finitely generated groups. Okay, so this one is 0, 1 cross 0, 1. Okay, so the Z2 is 0, 1, 0, 1. And then now to generate all the elements, you can find 0, 0. You pair them 0, 0, 0, 1. And then 1, 0, 1, 1. Okay, you can see that this group is of order 4. Yeah, order 4 Z2, Z2. Yeah, Z2, Z2 is of order 4. Okay, let's discuss this a little bit. I want us to look at this carefully. Okay, we're saying this group is not cyclic. Why? All its elements have order 2. If this group was cyclic, one of these would be of order what? will be of order 4 because it's of order 4. And one of these would generate the whole group. But all the elements of order 2, let us check this. Well, obviously, can add like 0, 0. Right, 0, 0 is 0, 0. What does it give? Component-wise addition is 0, 0. Anyway. Okay, now we can add this one. What about 1, 1? 1, 1 is 2, 2. 2, 2 is what? Is 0, 0. Modulo 2. Okay, so in the end, then we're able to see that this group is not cyclic because it has no single generator. Yeah, there's no single generator. Because the generator would be an element which you can add to itself. You can add to itself so that it generates the whole group, but it's not. So this group is not cyclic. Because this claim is that every abelian group is cyclic. This group is, of course, abelian. Because these integers, you can add them either way. You can change the order of the integers. Like 2 plus 1 is the same as 0 plus 1 is the same as 1 plus 0. Every abelian group is cyclic. Every abelian group is cyclic. So it is false. Because here is an example of an abelian group that is not cyclic because all its elements have order 2. And it is indeed abelian. Z2 cross Z2 is abelian. Next question. Okay, yeah, we're done. This one, every cyclic group is abelian. Okay, yay. This is powerful. So now they will bring it. Yes, this one is true. This one is true. Yeah, so this one, every cyclic group is abelian. Every cyclic group. I want us to spend some time on this. Every cyclic group is abelian. Okay, yeah. Yes, every cyclic group is abelian. Let's discuss this. So this is true. Okay, yeah, this one is a nice one to prove because it is true. So the true things are easy to prove. And to prove this, you suppose that G, the group, is generated by small g, is a cyclic group. Is a cyclic group. Okay, you suppose that, okay, we can, yeah, can even do it here. Right, you can even do it here and say, for example, okay, yeah, let's see. Suppose that G is a cyclic group. Is a cyclic group with generator G, then okay, yeah, it's cyclic group generator G, right? Like this. The G in the pointed brackets is the generator of the group G. And we then say, suppose G is a cyclic group with generator. Right. Okay, yeah, it's a cyclic group with generator small g. Okay, we generate a small g because the generator is the element. Then any AB in G, so you can take some AB in G, or of the form A is equal to G to the L all right, B to the power, right, B is some G to the power K for some integers. Okay, for some integers. Okay, let's discuss this one because for the cyclic groups, for some integers, LK. Can say L and K. Okay, for a group that is cyclic, every element can be written as a power of some group element. Okay, so this is true for the cyclic groups. Because what kind of a group is cyclic? Yeah, a group is cyclic if it can be generated by an element. So it's cyclic. Okay, so now then any A, B, and G can be written like this in power form. A can be written as G to the power of some integer. Maybe this one is like G squared equals some element, and this one is like G cubed is equal to some element for some integers, right? Now, if this is true, from here we obtain that so then we have AB. What is A? Is G to the L. B is G to the K. Okay, because yeah, the A is G to the L, the B is G to the K. Right, so you can take the same base. These have the same base, so yeah, we copy to correct 10 and we add the exponents. And then this is G to the power K plus L. And then this thing can be written as G to the Kth power, G to the Lth power. And this one here is exactly BA. Yup. And it means that AB is BA. AB is BA. Okay, so what have we proved here? Right, we have shown that every cyclic group, the G is cyclic, and we can write the power elements like that, or the elements in power form like that, is abelian. So that AB is BA in every cyclic group. Awesome. However, this is not the only way to reason. Let's take a look. There is sort of an alternative. There's alternative reasoning. Okay, alternative reasoning. If G has order n, if G has order n, then G is isomorphic to Zn. And so we shall discuss this. And so G is abelian. And so G is abelian. Very interesting module, this. And so G is abelian. If G is infinite, right, if G is infinite, then G is isomorphic to what? If G is infinite, then it is isomorphic to the set of all integers. is isomorphic to the set of all integers. And so G is abelian. And so G is abelian. Right, so we're saying alternative reasoning shows that if G is of order n, then G is isomorphic to Zn. And so G is abelian. So obviously we're then saying now we're starting with, we are looking at the fact that we have every cyclic group is abelian. So if G has order n, then it is isomorphic to Zn. And so G is abelian. If G is infinite, then G is isomorphic to Z. And so G is abelian. So we have shown, therefore, that these groups of order n themselves become abelian. And hence, therefore, indeed, it would follow that every cyclic group is abelian. Why? Because a cyclic group has order. Every cyclic group has some order, so that you can say the order of the group is n. And then now it means that there's a to the power n, that is the identity. And this A becomes the generator of G, so that G is generated by the element. And therefore we then say, if G has order n, then isomorphic to Zn. If it is infinite, it's isomorphic to Z. Okay, we're just discussing some of these intermediate results, but yeah, we're to delve deep into other things. Now, let's look at the 4 marks here. Every non-trivial group G has at least 2 subgroups. Yay. Yes. Okay, yeah, there's some groups we shall discuss. There's some groups we'll discuss. This is sparking another debate. But now, let me just hold my horses for now. But I want to say, right, every non-trivial group G has at least 2 subgroups. So this is true. First and foremost, we must state the truth or the falsehood. So this is true. Why is this true? It is true simply because 1 and G are always. 1 and G are always subgroups of G. Are always subgroups of what? Of G. True, 1 and G are always subgroups of G. So indeed, every non-trivial group has at least 2 subgroups, namely the trivial subgroup and the group itself. The trivial subgroup and the group itself. Okay, now, this is true. Every non-trivial group has at least 2 elements, has at least 2 subgroups, excuse. Right, it has the trivial subgroup and also the entire group G. But now, what can you say about the least number of normal subgroups of G? What can you say about the least number of the normal subgroups? Right. What can you say about the least number of the normal subgroups? Let's take a look. So now, we note first things first that now, if ever it happens that if G is not abelian, if G is not abelian, then 1 G and the center of G. And the center of G. The center, I think it's German, that's why I'm using Z for that. All right. What can you say about the least number of the normal subgroup of G? Okay, we're looking at the case where now if G is what? Right. Okay, we're saying that if G is not abelian, I'm wondering why the note is missing there. Right. If G is not abelian. Okay, we're here to play around with the questions, please, in this section, P chapter. Like now we are looking at those symmetries, group symmetries. Right. So now if G is not abelian, then 1G and Z of G are normal subgroups. Are normal subgroups of G. Okay. We'll discuss this. If G is abelian, then the center is the whole of G. And G has at least two normal subgroups. Two normal subgroups. Namely, namely 1 and G. Okay, now if G is not abelian, then the trivial subgroup in G and the center of G are normal subgroups of G. Okay, so yeah, we're saying for a non-abelian group, what are the normal subgroups that we're sure will always be normal subgroups? They're the trivial subgroup, G, and also the center. Right, these are the normal subgroups of any non-abelian group. What about if G is abelian? Then if G is abelian, then its center is equal to the group. And G has at least two normal subgroups, namely 1 and G. Name the trivial subgroup in G. So now, obviously, we're trying to answer this question. What can you say about the least number of normal subgroups of G? So we have seen, therefore, that for a non-abelian group, there are 3 normal subgroups that we're sure about. Now, if G is not abelian, then these are normal subgroups of G. So we have the center, we have the trivial group, and we have the group G. Every group G is a normal subgroup of itself. But of the trivial subgroup, it's a normal subgroup of G. But also the center of G it's what? It's a normal subgroup of G. But if G is abelian, then its center is the group. So that now it leaves us with 2 normal subgroups, namely the trivial subgroup and the group G. Okay, so we're good. Right, we're good. Okay, let us, yeah, so we have stated that question there. Let's get the next point. Let's look at the next point. Right, let's look at the next point. All right, now consider the following, consider the additive cyclic group, Z24. Now, for 10 marks, find all subgroups of Z24. For 10 marks, find all subgroups of Z24. And then next, we will draw the lattice diagram for Z24. Let's practice this one. Let's practice with this one. So now, first and foremost, to find the subgroup of Z24 using the, right, using what you call the fundamental. Using the fundamental theorem. Fundamental theorem of finite cyclic groups. Finite cyclic groups. We have that. Right, so we have that. Z24. Right, Z24 has exactly 8 subgroups. 8 subgroups of orders the positive Okay, we're writing here of orders the positive. Right, so of orders the positive, let's take a look here. The positive divisors of 24. Namely, what are the positive divisors of 24? The number 1 divides 24. The number 2 divides 24. Right. And then the number 3 divides 24. The number 4 divides 24. And then the number 6 divides 24. The number 8 divides 24. And then the number 12 divides 24. And then the number 24 divides 24. How many? 2, 4, 6, 8. Yeah, found 8 divisors. So now we make the following observation. So we make the effort to determine the unique. Right, we make the effort to determine the unique subgroup of each of these orders. Right. We continue. Okay. To determine. Okay, let us discuss this together, because we want to find all this here. We look at the divisors, there are those listed there. Okay, if those are the divisors, we have the following. Right, if those are the divisors, so to determine the what? The unique subgroup of each of these orders. Of each of these orders, recall that the order of the subgroup. Okay, we'll discuss these things. The order of the subgroup okay, the order of the subgroup generated by D would actually be the same as this product, DZ24. DZ24 is the order of the element of the element D bar, which is equal to D1 bar in terms of the conjugacy classes. Right. Which is the order of that particular element. Okay, we shall discuss this a little bit more, but I want us to analyze the implication of this here. I want us to analyze the implication of this here. Right, so we are first saying to determine the unique subgroup of each of these orders, recall that the order of the subgroup generated by D is actually, of the subgroup generated by D is the order of this element, the D bar, which is D1 bar. Now, I want us to, which is given, I'm going to write here, which is given by the formula, the order of D1 bar is equal to 20 out of D, 20 out of D provided, right, 20 out of D provided D divides 20. D divides 20. Okay, you're going to obviously have a very, no, that's 24. Right, so this is 24. Because we're dealing with Z24. Okay, we're dealing with Z24. If you're dealing with Z20, we just make everything that way. So we continue. Let us analyze this cautiously. Okay, let's analyze this very, very cautiously. Right. So let me see what we got. Okay, yeah, everything is actually above board. Right, everything is above board, just making sure that everything is above board. Right. So we actually, as we discussed this, we're trying to find the subgroups, and you'll see why all these things are justified. So, okay, now we then say at this point, clearly we have the following. So clearly, right. So yes, my dear. Okay, clearly, clearly the set that is generated by the sort of the conjugacy classes of 0 would actually be the same as the ones generated by the conjugacies of 0 in that form. Okay, obviously we have to spend time on the conjugacy classes, and also Z24 is the what? Z24 is the right. Okay, this is very important. So Z24 is the subgroup. Right, so Z24 is the subgroup of Z24 of order 24. Okay. So now then we have the order. Okay, let's look at the orders here. Because now we have dealt with those particular divisors. Right, having dealt with the divisors. Hello, my dear. Okay, somebody was just calling me there. Okay, never mind.
Okay.
Okay, right. Okay, I want us to discuss. This is very important. It's very important that we discuss this. But now obviously need to try and make sense of this. Now, and Z24, excuse, is a subgroup of Z24 of order 24. So it's a subgroup of itself of order 24. Now, we've already seen those divisors, 1, 2, and so on. There were like 8 of them. Now, let's look at the orders. Okay, let's look at the orders. So, for instance, if you look at order 2 would be 2, the order of D 1 bar. And let's say a little bit more about this. So the order of D1 bar would be the same as according to the formula we wrote before. Right, the order of D1 bar would be, because we're dealing with Z24, it's going to be 24 divided by D. So this is going to be exactly 24 divided by D. The D, or the D1 bar is going to be 24 divided by D. And if then really we are saying that the result is 2 here, that would mean that D is it's 12, because 24 divided by 12 indeed gives us 2. Okay, we're just practicing the notion of finding the subgroups of some of these specific groups here. So the subgroup of order 2 is what? Right, let us look at the group generated by the 1, 2 bar. We've already said that one. So the group generated by 1, 2 bar, we've already said the group generated by D is D Z24. So this one is going to be the group generated by 12 bar is the same as 12 Z4, Z24. Okay, you look at the nature of the way we argue these out, because these questions are going to be there, you know. So they're going to just change Z something to Z something, but now the expected presentation is surely this one. But now we've been able to get something. Okay, this is very important. What are we saying here? We are saying here the subgroup. Remember, I want to find the subgroup. So the subgroup of order 2 is this one. The subgroup of order 2 is 12 Z24. So we found the subgroup of order 2. Now we then continue, because we are looking at the divisors. But now, okay, yeah, it's gonna be very apparent when, because we said this line in the beginning is very, very important, because it says that now clearly the group or the subgroup generated by 0 bar and 24 is the subgroup of 24 of order 24. Right, it's a subgroup of 24 of order 24. Right, so 24 is a subgroup of itself. Right, so, and now we're able to see, therefore, that we have a subgroup of order 24. Why are we mentioning this? Because now we are looking at the fundamental theorem of finite cyclic groups, and we've found these orders. So now we have mentioned order 24, we have mentioned order 2, and we have mentioned order 1. Right, and then we must look at the other orders also. Right, so now we're going to mention the other orders, like order 3. Let's look at order 3, and then we can look at order 4. So if you look at order 3, for example, look at order 3. Order 3. Okay, it's fine. Order 3 would be 3 equals order. okay, which is 24 divided by D. So now, okay, if it's 24 divided by D, okay, because we're dealing with order 3, everything will start like this. But then all the problems start like this, and then just put the orders there. Okay, order 3, because they came from the list of those orders from the fundamental theorem of the finite, right, of finite cyclic groups. And so now we then have this. What number divides 24 divided by what gives us 3? We are sure that it is D equals 8. D equals 8, the divisor must be 8. But now what subgroup does this, you know, bring up or bring about? So the subgroup, okay, the subgroup of order, okay, because now, right, the subgroup of order 3, dealing with order 3 is, okay, because it is the 8 that, so we use this formula here, the D thing, use this formula, here is the formula. Right, we use this formula that, yeah, that D, that divisor, the group generated by that particular divisor, is actually D Z24. So in this case, the divisor is 8. So is the group generated by Z bar, and now which is 8 Z24. Where the bar relates to the notion of the conjugacy classes, than just an element, so that you have 8 Z24. So we found a subgroup 8 Z24, 24. Okay, now we go back to the list and then we check again. Okay, until we exhaust everything. Okay, because it's a practice. We've already done with 3, then we come to 4. Order 4. Right, so order 4. Okay. Order 4 would be as follows, right? It would be 4 equals the order of the 1 like this, 1 bar, which is exactly 24 divided by D. 24 divided by this 4. So now this must be 6. D, it must imply that D is 6, because it is 24 divided by 6 that is, yeah. So D equals 6, because 24 divided by 6 gives us 4. Right, and then the subgroup. The subgroup of order. Okay, the subgroup of order 4 is what? Because the D is 6, 6 bar, 624. Order. Okay, we're done with 4. We're done with 4 in the list. 6. Yeah, we're finishing. 6, 8, 12. Okay, and then we list them. Right, so now order 6 now. 6 is ODI. Remember, this question is going to come, but they're just going to change the 24 and put 20, you know, and put 18, something like that. So now you have this. So the 6 is exactly this one, which is 24 divided by D. You need to divide 24 by a certain number to get 6. And it can only be 4. Because 24 divided by 4 is 6. So D equals 4. And once you get the D, then we have the subgroup. The subgroup. Right, the subgroup of order 6. The subgroup of order 6 is generated by the the D bar, so it's generated by the 4 bar, which is 4Z24. All right. And then we have 8 now. Order 8. 6, 8. And then we have 12, and then we're done. And then we just list the subgroups. Okay, yeah, but we have listed them somehow because it's under exam conditions. You don't need to write a lot of repetitive things. Order 8, and then now it's order 8. Then what you do, you put 8, which is the order of the D1 bar. 24 divided by D, and this implies that there's a number that divides 24 to give us 8, and the number is 3. The subgroup. The subgroup of order of order 8 is what? Subgroup of order 8 is 8 bar, which is 8. No, it's 3 bar because the divisor is 3. The divisor is 3, so it is exactly 3 bar. And then from 3 bar, it is 3 Z24. It is 3 Z24. Okay, let's check. Okay, yeah. Let me see. Order something else. Order 12 now. Order 12. Okay, all these are the divisors of 24. Order 12 would mean 12 equals OD1 bar, which is 24 divided by D. Which means that D is equal to the number 24 divided by a certain number. It's 12, and it's only 2 that divides 24 to give us 12. The subgroup. Right, so the subgroup is the following. So the subgroup of order 12, the subgroup of order 12 is what? Okay, the divisor is the 2, and this becomes 2Z24. 2Z24, and this is what? Yeah. Okay. We've found all of them. Find all subgroups of and thus you can write them in red here. Hence the subgroups of Z24, counted, there must be 8 of them, are as follows. They are, you can write them in any order, 12, 12, which is 12 Z24, in any order, please. So we have this one here. It might not be exactly the order in which you wrote on the previously, but they're all, we're just listing them. So it's 6, 24, 3, 3Z24, okay, 8 bar, which is 8 Z24, 4 bar, which is 4 Z24, 2, which is 2 Z24. How many did we list so far? How many have we listed? So it's up to 24. We have 1, 2, 3, 4, 5, 6. Then we need 2 more. Right. So And the two more are the ones we stated in the beginning. What are they? Right, so we have stated in the beginning that, for example, clearly this one, the trivial one, and also 24 is a subgroup 24 of order 24. So in other words, we would have Z24, and it is the subgroup of order 24. And now, I want us to write this in the usual notation. So because now we have exactly the 0 together with the trivial subgroup, but also this one, Z24 is the subgroup of 24 of order 24. In terms of the notations, so we also have Z24, but now you can write it in terms of the notation, because if this is 24, order D1 bar, right, it's going to be 24 divided by what? It's going to be 24 divided by 1. That means D is 1. That means in the notation here is going to be 1 bar, is 1 bar, 24, like this. Then it gives us another subgroup, but also the other subgroup, if you deal with this one, we mentioned it, 0 bar, 0 bar, like this. Okay, so this one here is the one we actually mentioned. So now if it is of order 1, so you would say 1, order 1, order 1. Okay, this one is order 24. Okay, order 1 is going to be 1 order D1 bar. Okay, so if it's 1 here, it's going to be 24 divided by 24, which means that D itself, and that would mean that, okay, this is for the top one. For the bottom one here, it would mean that obviously here that our D is 24, because you want to get 1. And that means that you can view, or actually the D, which is 24 bar, and now this would be the same as what? Right, so it would be the same because it would be the same as 24, yeah, Z24. Yeah, and this is true. Why? Because this Z24 now, it's actually producing this one. It's producing zeros, modulo 24. Because what is Z24? Z24 means that, okay, we'd have the 0, the 1, the 2, but you know, the 3 up to 23. But now you have all this, and then you multiply every element by 24, and then it becomes 0. 24 by 0, it's 0. 24 by 1 is 24, but 24 is congruent to 0 modulo 24, and so on. So yeah, so obviously this one here, so this gives us like 8 of them, of the subgroups we found from the divisors. So you'd have this one, and say, for instance, that's a 1 there, that's a 2 there, that's a third subgroup, that's the fourth subgroup, fifth subgroup, sixth subgroups, seventh subgroup, eighth subgroup. Okay, we found 8 divisors, and therefore, yeah, I know that we're moving to the next question. We're just discussing this one. Okay, I'm trying to create familiarity with the kinds of questions that we are sure you're gonna meet, no matter what. So now this is exactly, and now we counted 1, 2, 3, 4, 5, 6, 7, 8. According to the fundamental theorem of finite cyclic groups. Okay, for this we use the fundamental theorem of finite cyclic groups. That means that how do we use it to find all the subgroups, this fundamental theorem of finite cyclic groups? we have that Z24 has exactly 8 subgroups of orders the following. Right. So, and so we actually have this because these numbers, this list of numbers is the list of numbers of the divisors. The divisors. Yeah, these numbers of orders this. The positive divisors of 24, namely this. So we actually wrote the positive divisors of what? Of 24. And now for every positive divisor, then we have a what? A subgroup of Z24. Let's move to the next point. All right, we're here to get to the section that the chapter 3 and discuss those symmetries, group symmetries. All right, I want us to look at if you consider the following additive subgroup groups here. Draw the lattice diagram. Let's draw the lattice diagram of Z24. Right, so there's something we use here to draw the lattice diagram. So as we're discussing, I said already, we're here to look at so to draw the lattice, diagram, we use that K bar becomes a subset of M bar if and only if M divides K. If and only if M divides K. Right. If and only if M divides K. Now, let's say something here. So we're going to write the following. Okay, so we're going to write the following. Let's write, I want to write the subgroups according to the list. It's fine. So let us write the following, for example. We can write 2 Z24 is 2 bar 3. Z24 is 3 bar 4. Z24 is 4 bar 6. Z24 is 6 bar 8. Z24, the subgroup we got, is 8 bar. Okay, what else are we missing? Also have 12. 12, Z24 is what? Is 12 bar. Okay. And then we also have 24. Stated that one. Right, and yeah. But I can write like this. Let's not write funny things here. It can be written like that. But for the purposes of this course, it's popular to write it like this. And it means that one of order 1. And then we also have this one, Z24 itself. Okay, so with this notation, okay, in any order 1, 2, there must be 8, 3, 4, 5, 6, 7, 8. Okay, in any order, there are 8 like this. Now, let us think together. So now, you start from the smallest one. So we're going to start from the smallest one. We're starting from Z bar. And this Z bar can be seen as what? As 24 Z24. Now, this one is the one of order 1. But this order 1, as said, to draw a lattice diagram, we use the fact that this subgroup generated by K bar is a subset of this one if and only if M divides K. If and only if there, you can use the bigger one. Okay, the one that is sort of bigger divides the smaller one. It's counterintuitive, but yeah, in that sense. Okay, so now let us do this. So now we start with here, and we then say the smallest one, 0 of order 1 divides. Okay, because now if you want to put a bigger one up here, this bigger one you put up here must be such that it divides, this order divides the smaller one. Okay, let us look at exactly that part there. Now, if we decide to put, let's do this. Okay, I want to come here. I want to mention something here. I want to mention something here that is important. I want to mention this something I wrote. Okay, I want to mention something here that is important. So obviously here we can see that it's order 6. It's order 6, and therefore obviously we got the divisor there. And the subgroup became exactly that one. And then order 8, you had actually the 3 is the divisor. Okay. And there's something I'm sure we actually shall drive towards. So let us look at the smallest to the largest. Okay. Now let us look at your 12. Z24 together with 8 Z24. Okay, let's analyze these so that you can be able to order the subgroups very well. What then do we have here exactly? We are able to see clearly that at this point here, you have the 12 Z24, and this one here, the 12 Z24, mention something. Right, so the 12 Z24, there's that one, right. Right, so if you have the 12 Z24, we wrote it, I jumped it. This is 3 Z24, 4 Z24. Okay. Right, so yeah, it's this one here. Yeah, it's the one we wrote first of order 2. So if you look at the 12 Z24, what is the 12 Z24? So the 12 Z24, we actually can see that its order became actually the order 2. And we are using the order divisibility, ordering. So now, which means that now the 12, very interesting. So you can see that we're going to use this criterion, which is going to be easier. So when you put the numbers here, you can say 12 divided by 24 divided by this number, and then gives the order, and then you can quickly do that. And then 24 divided by 8, would give order 3, so that you don't keep moving back and forth. So yeah. So now at this point, then you can see that this one here would immediately be seen as order 2, because 24 divided by 12 is 2, and also 24 divided by 8 is what? Is 3. So we have that ordering there. Next. So we also have here, if we position 6 Z24, and you also put 4 Z24. Right? So you put 4 Z24, 6 Z24. Now this one here is order what? 24 divided by 4 is 6. And also this one is 24 divided by 6, which is 4. What are we seeing here? Okay, okay, can I write the orders in a color? I want to write the orders in a given color field. Okay, so now the order is 2 here. Okay, it's gonna be so confusing, too many numbers, but I'm gonna write order 2. Right, so I'm gonna write order 2, and then order is divide 24 by 6 to get a 4. And here divide 24 by 4, you get a 6, so it's order 6. This one divide 24 by 8, you get 3, so it's order 3. All right, so I'm going to remove exactly this. I'm going to actually write it somewhere at the top, but yeah, I want to create a bit more space to complete the diagram as it goes up. And I want us to just sort of try to discuss this because it's very important. And I know very well now the question is, can all students get the same sort of diagram from time to time? Okay, now there's 12. Okay, I want us to look at the fact that we say, we use the fact that K bar is contained in the subgroup generated by K bar is contained in the subgroup generated by M if and only if. Okay, so you're going to use it to just analyze the set containment so that you can actually get very consistent results if and only if M divides K. So yeah, if we look at this. Okay, now we are then saying here, we're looking at the orders. Now, and let me write here and then say order 3, order 2, order 1. Now, 2 divides 6. Right, 2 divides 6. Like that. So because 2 divides 6, we link them up. 2 divides 4. 3 divides 6. 3 divides 6. Okay. But also 1 divides 3 and 1 divides 2. But 2 divides 6. But also 2 divides 4. 3 divides 6. But obviously 3 does not divide, 4 does not divide 2. Okay, I'm trying to, yeah, we're finishing, please. I know I can see the time. Next, we're analyzing the order, the divisibility. So we grow it up like this. Now, okay, we look at the subgroups here. So 4 divides what? Right, we're able to see that 4 divides some numbers, like the numbers we're seeing here. And 4 would divide 8. 4 divides 8. because this one you can see is order 8. Why is it order 8? It's order 8 because 24 divided by 3 is 8. Now, so 4 indeed divides 8, but 4 does not divide the others. Now, we have here 6. 6 divides 12. 6 divides 12, because this one is order 12. So 6 divides 12. Okay, now 24. Okay, let's see. But also 4 divides 12. 4 also divides 8. But 4 divides 24. Order 24, yeah, but that one is in the path. So yeah. So this would be the lattice diagram of Z24. Okay. I've seen the time, and we're just breaking ice today. Okay, today we're just breaking ice. I just thought I need to speak about this, but I thought I need to speak about this because I was looking at the assessments and the things they ask. Because as much as we can digress and spend time on a lot of things, but the question is, how do they ask the questions, and how they assess the module becomes so important. Any remark, any question? Because we need to meet again, but we agreed that we actually would meet. We need 2 meetings every week, right? So obviously we've met now, but now we need to meet again. We'll discuss. You'll let me know. It's up to you. By and large, if you suggest the date, then we can always try to configure our program and make sure that we are more inclusive. So, right, it's just necessarily a thought.